All right, Chapter 9, test preparation. A couple quick things about this Chapter 9 test. Chapter 9 is about right triangles and trigonometry. So pretty much every single diagram you see is going to look similar to this, where you have this little perpendicular right angle somewhere in there. That is going to be the standard throughout this entire chapter. We're just going to be using different strategies to solve for different pieces. There's going to be a lot of solving for missing pieces based on information that we see. I'm going to show you the order of the problems exactly as they'll be presented tomorrow. I will remind you as well, in this upper left-hand corner, I give you a section reference so that if you do need to kind of look back at your notes, give yourself a little confidence as you work through the test, that will tell you where to look so you can find that kind of information. All the examples I'm going to be doing today are pulled directly from the notes for each of these sections. So for instance, this problem was one of the examples from the section 1 notes on the Pythagorean theorem. That will end up being the technique we use here. And so the purpose of this video, again, is to not only show you what types of problems you will see, it's going to give you strategies and references for how to look up ways to attack the problem. I'm going to show you the type of scratch work I'm expecting to see for each problem. So for those of you that like to do things in your head, this would be good for kind of seeing like, oh, that's how I show my work. Okay. And then I'll ultimately talk about how things might be presented differently in case you see it differently presented on your test tomorrow. Okay, let's jump right in. So our first problem tomorrow is going to be one of probably the most comfortable of the problems that you'll get tomorrow. And that's going to be a Pythagorean theorem problem. You'll be simply given a right triangle like you see here on the page. You're going to be asked to solve for the variable. One of the 3 legs will be given as that variable. It could be either leg, it could be a hypotenuse. It really doesn't matter. But if you're ever applying the Pythagorean theorem, you definitely want to be aware of which of the 3 sides is the hypotenuse. The hypotenuse is always opposite the 90-degree angle, and that matters because when I set up my equation, I will always take the leg squared plus the leg squared. The 2 legs are what create the 90-degree angle. So here that would be 7 squared plus x squared. That's just simply taking what was in both those locations. But this is the important piece. Because it's by itself, the hypotenuse, the most important side, the longest side length in this triangle, the one opposite the 90-degree angle, has to be the side that it equals squared. Okay, that's really the only hiccup that a lot of students get when it comes to setting up a Pythagorean theorem. They just do some random collection of things that are squared. Okay, it has to be leg squared plus leg squared equals hypotenuse squared. So as long as you get that right, then it's just arithmetic. All right, well, this stuff can be done on a calculator. 7 squared or 7 times 7 gives me 49. My unknown squared stays unknown squared. 14 squared or 14 times 14 would come out to be 196. Don't be a hero. Use calculators when you need them. All right, at this point now it's just solving for variables, so I need to subtract this piece over to this side. Again, depending on where the variable is located, maybe there's a different strategy you use. In this case, I need to subtract 49, so I'll get x squared by itself equaling 147. Done this a couple times already, so don't be too impressed. I know this number off the top of my head. Okay, one last thing to do technically here. I need to take the square root of both sides. I'm going to get x equals the square root of 147. For whatever reason, when people do Pythagorean theorem, a lot of people forget to do that last step of that. It's going to be the square root of these values. That'll be an important last step there. Now, technically speaking, this is what we would call the exact solution to that side. So what is the exact solution here? What does that mean? That means like no rounding, no approximating. There's no decimal point that we've like rounded down or up or whatever it might be. In this case, the length of this side is the square root of 147. This is an exact solution. Also, technically speaking, this can be reduced. This can be simplified, kind of like a fraction that can be simplified. This is a reference to a previous chapter. Let me just briefly go through this. In a calculator, if I were to attempt doing the square root of 147, as such, notice I get this gross decimal. First off, that actually answers this question. So not only are you going to be tasked with finding a missing side length, you are then going to be asked, does this represent a Pythagorean triple? So just briefly, this is referenced in section 1. What is a Pythagorean triple? It's actually a very simple thing. It's not very significant. It just means that all 3 side lengths of a right triangle are whole numbers. So had I done this result and gotten some friendly whole number result right here, then it would have been a Pythagorean triple. However, as you can see, I get a gross decimal result. Doesn't mean it's not a right triangle. It just means it's not a Pythagorean triple, because this ended up with a decimal result. So that part of the question is answered. Okay, and if you were asked to approximate the solution to some decimal point, that number I would round to whatever it asked me to. But on the test, you will be asked to then reduce or simplify this. So I know now that 147 is not a perfect square as it is. So the next thing I would check is, does a perfect square divide evenly into 147? This is a technique that we learned in a previous chapter. Again, what are your perfect squares? 4, 9, 16, 25, 36, 49, 64, so on and so forth. Okay, basically each of the counting numbers squared. Okay, so you're basically checking to see, do any of those divide evenly into this? I'll go ahead and skip to the punchline. This was one that we had again in our section 1 notes. There is a perfect square that divides evenly into 147. It's not a particularly friendly one, but it's still one nonetheless. And that is the number 49. So for the record, 49 times 3 is the same exact thing as 147. So I've not actually changed anything here. This is still the square root of 147. But the reason why I split this up, and this is where, again, I'll reference what we did in a previous chapter when it came to reducing radicals, is I'm going to be using one of the properties, saying that now I can take the square root of each of these elements separately. And that matters because this piece right here, that 49 that I chose, is one that I can take the perfect square of. Square root of 49 is 7, and I'm left over with this radical 3. So this would be my fully simplified, reduced version of this. If you stopped here, for the record, you just wouldn't get full points. You'd get most of them. It's just that being able to reduce down to the fully simplified version will get you what's full points. So again, this is correct, but this is fully simplified. And again, to answer that other question about, is it a Pythagorean triple? Not a Pythagorean triple. Why not? Because this resulting side, that 7 times the square root of 3, is not a friendly whole number, meaning it's not a Pythagorean triple. Pythagorean triples are reserved for 3 whole number results. Beware that if you did get just a nice friendly whole number result as that side length, then you'd be done for solving it. And then you would just simply say, yes, it is a Pythagorean triple. Okay, but that's problem number 1, referenced in section number 1 on the Pythagorean theorem. All right, problem number 2. Problems numbers 2 and 3 are a little tedious, I will say. So bear with me on these ones. All right, this one is going to be referenced in section 2. Section 2 was our section on special right triangles. What does that mean? Okay, so special right triangles, there were 2 of them and we talked about. There was the 45, 45, 90, the what we would call the isosceles right triangle. And then there's the 30, 60, 90 triangle. Okay, so you're going to be asked with doing the following. You're going to be asked to find variables. Okay, and there'll be 2 that you are solving for. And just like in the last problem, I'm going to be looking for exact solutions. I'll make sure I remind you of that on tomorrow's test. And then you'll be given some special right triangle. I will tell you right now that of the 2 special right triangles, you will get a 30, 60, 90. 30, 60, 90. Okay, so there's our right triangle. And here's the piece of information that's going to give away which of the 2 special right triangles we're working with. I'm going to tell you what one of the other 2 angles is. For instance, I might tell you that, hey, this is 60 degrees. How do I know it's a 30, 60, 90 now? Well, first off, built into it is that 60. By the Triangle Sum Theorem, the only amount of degrees left over for this angle is 30, thus making it a 30, 60, 90 triangle. Okay, and so just to kind of give us a little reference point off to the side here. Okay, because I'm going to draw this a couple times. Wow, that was really sloppy. Redraw. Okay, so just as a little miniaturized version, I'm just going to reference this. You'll see why in a second. It's going to get a little busy here. So if that's 60 degrees, that's going to force this one down here to be 30 degrees by the Triangle Sum Theorem. And let me come back to what you're going to be given. Okay, so you'll be told that one of the angles is going to make it a 30, 60, 90 triangle. And then you'll be told one of the side lengths. In this case, in this example from our section 2 notes, we were told that this bottom leg here was 9 units long. And our job here was to solve for the following missing pieces. Yours will be similar. Okay. So what was the significance of the 30, 60, 90 triangle? For the record, all right triangles have proportional sides to all the other ones that are like that. And so that the whole study of that is what makes trigonometry, which sine, cosine, and tangent we'll explore in future sections that we'll talk about here in this cheat sheet. But the reason why the 45, 45, 90 and the 30, 60, 90 are brought up specially in section 2 is because they have a nice friendly collection of ratios. Namely, in the 30, 60, 90 triangle, the 30 degrees is the smallest side, meaning that the side opposite this side right here, which in this case is this side right here, okay, this shortest side length, we're going to use this as our standard of measurement. We'll give that the ratio designation of 1. In other words, if this is 17.8 miles long, we're going to multiply it by something to get this length, and we're going to multiply it by something to get this length. So the ratio here is that in a 30, 60, 90 triangle, whatever length this short leg is, I'm going to multiply it by 2 to get the length of the hypotenuse in this 30, 60, 90 triangle. So for instance, if this was 17.8 miles long, I would multiply that 17.8 by 2 to find the length of the hypotenuse. What would I do to find the length of the side opposite the 60 degrees? This one has a square root of 3 ratio. Okay. So in this case, again, if this was 17.8 miles long, this short leg here, if I wanted to find the length of the hypotenuse, I multiply it by 2. If I wanted to find the length of this leg, I would take this 17.8 miles and multiply it by whatever the square root of 3 is. And that's the ratio of sides for this special right triangle. And so again, you will get a 30, 60, 90 triangle on tomorrow's test. So it'll be similar to this, even if some of the numbers are different. Really, the only number will be different is whichever leg I give you, it will not be 9. Okay. So of the 3 sides, you'll get one of the lengths and you'll be asked to solve for the other 2. Okay. So let me use the technique that I actually used in the solution sheet that I did for the section 2 notes. I designated this short side, this standard length side. I called this side length A. Okay, meaning that A value, in this case, is going to be x units long. I'm going to double that length to find the length of the hypotenuse. So y is going to be double the length of x. You'll see why I'm giving them these designations in a second. It makes it a little bit easier for writing the equations in a second. This side is the square root of 3 times a. Okay. So another thing you could do here, I use this technique. Another thing you could do here is just skip this and just be like, all right, well, instead of just writing a every time, why not just replace a right now with x? So this is going to be 2x. This is going to be square root of 3x. There. So if this is my standard of measurement, the 1 ratio side, I'm going to double that length to find the length of the hypotenuse. I'm going to multiply that length by the square root of 3 to find this side. And that becomes important because I don't know actually what this length is, but I do know this length. In other words, I can actually solve this equation for x. Let's do that right now. And that will end up being used for solving the other unknown side. So as long as you can set up this ratio, whatever the short side is, okay, and it worked out this way where it ended up being x. I will tell you that on your test tomorrow, it might not be that. Hint, hint. So whatever your short side is, whether you know the actual number or not, like in this case, the hypotenuse has to be twice that length, and the side opposite the 60 degrees has to be square root of 3 times that length. Again, whether you know the length of the side or not. But here's how I can go about actually solving, say, this equation and figuring out the first of my 2 variables. So let's actually solve this equation. So here I have the square root of 3 times x equals 9. Well, if I want to get x by itself and thus solve for it, I need to divide both sides by that square root of 3, and I'm going to get the following. So for the record, 9 over the square root of 3. I'm about to get into how to rationalize this and stuff. It might not be as complicated for you at this point in tomorrow's test, but at this point, this is just referencing previous chapters. But this would be how I would go about solving for the variable. You may get a friendlier result. be aware of that. But at this point, I have to follow a certain rule that tells me I cannot have square roots in the denominator. So in this problem, that was, again, this is pulled directly from notes, so it's kind of a little scary looking. I had to multiply top and bottom by that denominator. This reduces to 1. This is called rationalization. So if you ever end up with a radical in the denominator of a fraction, you can multiply top and bottom by that same denominator, and it's going to get rid of the square root. So in this case, that's going to give me x is 9 square root of 3 over the square root of 3 times the square root of 3, but the square roots end up canceling, thus getting rid of the radical in the denominator. And then this, I would just check to see if it can reduce. This one does. 9 over 3 reduces to just 3, radical 3. So what does x equal? X equals 3 times the square root of 3 in this case. Again, this process right here is referencing previous chapters. It will not necessarily be this complicated on tomorrow's test. But so great, I have solved for one of my variables. I do need to solve for the other one, the y value here. So here's where I'll scroll back up a little bit, back to our diagram. I'll point out that y, this hypotenuse length, is equal to 2 times whatever x equals. Well, I've just solved for x. X is that 3 times the square root of 3 in this case. So I just have to double that in order to figure out what y is. So just briefly showing that off to the side here. Okay, I'll use, let's use blue. Okay, so if 2x equals y, all right, well, I already know what x is, so I can substitute that in, and I'm going to get 2 times that x value equals y. That x value is that 3 radical 3 that we just solved for. And so 2 times that 3 radical 3 will give me my y value. That ends up becoming 6 radical 3. There we go. There's my y. All right, so even though the numbers looked a little scary, that's the process you'll go about for solving your special right triangles. Great, that's problem number 2. A little tedious, I know, because this one, the example that we used in the notes was tedious. It had tedious results and stuff, but let's move on. All right, next problem will come from section 3. Surprise, surprise. Section 3 was on our similar right triangles. This one also is a little tedious, to put it kindly. The section 3 on special right triangles had very unique diagrams. I'm actually going to demonstrate 2 possibilities for you because you're going to get one of 2 types of questions. Essentially, it'll be the same one. Solve. Solve for a missing piece. Okay, solve for x. Okay, just like in the previous ones where you're finding x. But you're going to get one of the 2 types of situations. Okay, we learned about 2 different theorems in section 3. There was the altitude theorem and the Leg theorem. I'm going to demonstrate both for you now. You will get one of these 2. Again, I wanted to emphasize. So I'm going to show both of the examples that we did in section 3. Okay, we were given a right triangle. Surprise, surprise. All right, and I'm showing you multiple orientations because it really doesn't matter how it's oriented. The same rules kind of apply. But then they're going to be chopped with these altitudes. Okay, and this may start to look familiar. And they're altitudes because they also make right angles with their opposite side. But we end up with this situation. In both cases, we have a diagram of a large right triangle that's split into 2 smaller right triangles. So large right triangle, 2 smaller right triangles. And then you're going to be given information, limited information in both cases. So for instance, in this case, you might be told, all right, this is x, this is the piece you're solving for, and then maybe like this piece here is 6, this piece here is 3. In this case, maybe this is the piece you're solving for, this piece here is 2, well, this is dead, and this piece here is 5. Okay, there we go. I'm going to toss this now. Okay, so again, you're only going to get one of these scenarios. And by the scenarios, I'm talking about where the information is located. Notice in this guy, my unknown piece is this altitude. Okay, in this one, we're going to be using the altitude technique, the altitude theorem for geometric means. In this case, notice my unknown length is one of the legs of the major triangle. Now, it will be either of the legs. It won't necessarily be this one, but the techniques are similar. Okay, one we're given our unknown in the leg, one we're given our unknown in the altitude. You will see one of these scenarios. So here, let me just jump right to what the shortcut ways, because in section 3 we learned a couple of shortcuts based on these two scenarios, being altitude and Leg theorem. If I'm asked to solve the altitude squared is equal to the product of these two pieces. Okay, in this case, that x squared is equal to 6 times 3. Now, very briefly, and here's where it's important to pay attention, you might not necessarily be given both of these pieces. Maybe I give you like a piece and then the whole length. In that case, I'd have to do a little bit of a pre-step where I'd say like, well, I need to find the length of this little piece first. So if I told you like the whole length here was 9, and then I told you this piece here was 6, that leaves 3 left over here. So that'd be another way of about it given to you. Or maybe vice versa. Maybe I told you the whole major hypotenuse here is 9. This little piece here is 3. So what's left over here for this piece? Okay. In either case, these two pieces multiplied by each other will equal the square of the altitude. There's a little bit of a complicated backstory as to why that is. It has to do with the fact that in this right triangle, there are 3 right triangles that are all similar to each other. I'll let you refer back to section 3 if you want to investigate that a little bit further. But suffice it to say, if I'm solving for the altitude in this case, the altitude squared is equal to the product of these two pieces. And again, I'm emphasizing that because maybe I don't give you the two pieces. Maybe I give you the whole length and one of the pieces that you then have to backtrack and find the other one. In either case, this is what we would end up with in this scenario. And at this point, now it's just arithmetically solving for it. Do the multiplication, I would get x squared equals 6 times 3 or 18. Take the square root of both sides. X is equal to the square root of 18. Just like we did before, I just have to make sure I simplify it. 18 I can't take the perfect square of, but a perfect square does divide into it, and that would be 9. So x is equal to the square root of 9 times 2. And that can be reduced to 3 radical 2. So what does x equal in this case? 3 radical 2. Okay, so now to the other scenario. Again, you maybe get that one where you're solving for an altitude. Maybe you get one where you're solving for a leg. Okay, so in this case, if I'm solving for a leg, it's going to start similarly, but then it's going to be a little bit different. I'll start with whatever leg I'm solving for. It could be either. I'll talk about the alternative way in just a second, but maybe it's this leg that I'm solving for, like in this example. I would take that leg and square it, just like we did at the altitude, the missing piece I'm trying to solve for. And now I'm going to be multiplying two pieces. However, they are not these two pieces. Let me explain. That maybe came out confusingly. So I'm going to be multiplying two things together, but I'm not going to be multiplying, like in this guy, these two pieces. Notice that of these two pieces, one of them is closer to the leg I'm solving for. Namely, this 2 is right next to this leg I'm solving for. I will be multiplying that piece by something. Now, here's where I'll talk about the other alternative. Maybe this was the leg I was solving for, in which case notice that the 5 would be next to that leg. If that was the case, it'd still be leg squared is equal to 5 times something. Okay, so again, this case it's different because I'm solving for this leg. The 2 is next to it. That's going to be the first thing I'm multiplying. This is where it's going to get a little different. Now I'm going to multiply by the whole hypotenuse. The whole hypotenuse. So in this case, I actually have to add these two guys together. So if I know that this whole thing is 7, many of you would just be like, all right, well, that whole thing is 7, and then you'd be fine. In this case, just to show you that, like where that comes from, I have to add those two pieces together. Okay. So again, the difference here with solving for one of the legs, it's the leg squared, whichever leg I'm solving for, it's the leg squared. And then the piece that's directly next to that leg, in this case, it's the 2. Had I been solving for this leg, it would have been the 5. But it's the 2 times the whole hypotenuse. And so that's where that 2 plus 5 is. So that arithmetic is really quick. Many of you would just skip right to this. It's 2 times 7. But I wanted to make sure you understood where the 7 came from. And then just to finish it out, just like the last problem, 2 times 7 is 14. I take the square root of both sides. Y is equal to the square root of 14. I can't take the perfect square of 14. No perfect square actually goes into 14, meaning that this would be my final solution for that variable. Okay, again, I want to emphasize it will be one of these two. Okay, so if you get the altitude one, you're not going to get the leg one. If you get the leg one, you're not going to get the altitude one. But I wanted to demonstrate both just so you could see it. Okay, that was the last of the tedious problems, I will say. But we still have a few problems to get through. So our next sectional reference will come from section 4. The next 3 problems are going to come from section 4. And you may be feeling like, oh my God, like 3 problems and there's still more in the test. This is where the problems actually become very fast. So this next series of problems will actually be referenced in both section 4 and section 5, I should mention. Section 4 and section 5. Section 4 was the introduction of our first trig ratio, namely the tangent. Section 5 talked about the sine and cosine. Okay? And in these cases, you are going to be asked to solve some trig ratios. And I'll show you what those 3 questions will be in a second. Okay, so for instance, you may be asked to solve, well, actually, before I get to those questions, I'll first draw the diagram. You'll be given a right triangle. Surprise, surprise. This example is pulled directly from our section 4 notes, by the way. And I'll label the points. RST. It won't be RST necessarily on your test tomorrow. It might be different letters. It doesn't really matter. But then I'm actually going to give you the lengths of all 3 sides. Okay? There'll be different numbers, but you'll get a triangle with 3 known side lengths. This is not Pythagorean theorem. I'm not asking you to solve for unknown side lengths. But we will be asked to do a trig ratio based on this triangle. Okay, so you're going to get 3 questions here. The first question, so this is actually question 4 on your test. You're going to be asked to take the tangent of some angle. In this case, let's say find the tangent of angle S. Okay. That's question 4. Question 5, you're going to be asked to take the sine of some angle. Let's say a different angle, like angle R. And then for question number 6, you're going to be asked to take the cosine of some angle. Let's say you do the cosine of angle R again. Okay, but these will be question 4, 5, and 6. Find the tangent of some angle, find the sine of some angle, find the cosine of some angle. You'll be asked to first find it in fraction form, and then you're going to be asked to then approximate it or round it to the nearest hundredth or 2 decimal places. Each of these 3 is actually super fast, but the following will be very, very valuable to know. This mnemonic. So, ka, toa. Make sure you have that headline somewhere for these problems. Problems numbers 4, 5, and 6. You're going to use SOHCAHTOA. The S, C, and T refer to sine, cosine, and tangent. The O's, A's, and H's refer to which of the legs I'm going to be putting in that ratio. O is for opposite, A is for adjacent, H is for hypotenuse. All right, so for tangent, that's TOA, so opposite over adjacent. So first, identify where is angle S. There's angle S up there. So what is opposite over adjacent? What's opposite angle S is that 80. What's adjacent to angle S? That 18. There's the tangent of angle S. Just make sure you reduce that fraction. 2 goes into top and bottom. That would become 40 over 9. So there's my reduced fraction, tangent of angle S. In a calculator, that is 40 divided by 9. I'll just tell you right now that round to the nearest hundredth is 4.44. Sometimes having exact fraction answers is more valuable. Sometimes rounding it is more valuable. So in this case, you have to show me both. That's it. All right, so that's problem number 4. Problem number 5, sine of angle R. Sine is so for opposite over hypotenuse. So where is angle R? That's this guy here. So opposite over hypotenuse. What's opposite angle R? That 18. What's the hypotenuse here? Well, the hypotenuse is the same wherever you're at in this triangle, and that's this 82 length here, the side opposite that 90-degree angle. Reduce that fraction, 2 goes into top and bottom, and you get 9 over 41. That's the sine of angle R. If you were to plug that into a calculator, round to the nearest hundredth, you would get 0.22. Okay, again, that can just be a division problem to find that decimal result. All right, cosine of angle R. Same angle, but now for cosine, I'm doing the adjacent over hypotenuse, the ka part here. So it's adjacent to angle R, this 80-degree side, or 80 length side. And what's the hypotenuse? The same hypotenuse as before, that 82. Reduce your fraction. This will reduce to 40 over 41. Round into the nearest hundredth, that would come out as 0.98. Again, emphasize I could have done that in the calculator for you guys, but I'll trust that you can do those button mashing things. There's problems 4 through 6. As I said, pretty fast. You're just basically reading which of the sides go into the correct spots in the in your fractions. Again, SOHCAHTOA will be valuable for that. That's what we'll have from section 4, section 5. Let's move on to our last problem, or last 3 problems technically. I'll show you what I mean. All right, this last 3 set of problems will come from section 6. Section 6 was on solving right triangles. And so in solving right triangles, I will give you the following example. You are going to be given a right triangle. This is pulled directly from our section 6 notes. It may look like this. There'll be similar kinds of information. Right triangle, I will label the points. So we'll call this triangle G, H, J. And then you'll be given pieces of information. In this case, we were told that the hypotenuse is 13 units long, and this angle H is 25 degrees. Okay, so what are going to be the 3 questions about this triangle, this diagram? You're going to be asked to find the 3 missing measurements in this triangle. In this case, based on the information I'm given, you may be asked to find the measurement of the missing angle. In this case, angle G. There are 2 side lengths I don't know here, so you're going to be asked to find those missing side lengths as well. So in this case, there's side GJ and then there's side HJ. This would be like question number 7, 8, and 9. All right, so I'm just expecting to see work for each of these. So in other instances, some of you may be getting something where I give you 2 of the side lengths. This is like what I went through yesterday for our section 6 summary. Maybe I give you 2 side lengths, in which case you use Pythagorean theorem to find the third. In this case, I have 2 angles given, so I'm going to use Triangle Sum Theorem to find my missing angle. And then, again, you're going to need to use trig at some point. So let's go ahead and start with the obvious of the 3. Let's go ahead and find angle G. I'll use Triangle Sum Theorem because I know 2 of the angles. So the work for that would be like me saying, all right, 25 degrees plus that 90 degrees. Those are the 2 angles I know here. Angle G is the one I'm solving for. But all 3 of them together have to add to 180 degrees. That's the Triangle Sum Theorem. 25 plus 90 is 115. I would subtract that from 180 to figure out what's left over for angle G, and I would find that angle G is equal to 65 degrees. Pretty quick. All right. Again, whether you're using Triangle Sum Theorem, like in this case, or if you had 2 sides and you're finding the third side, so you're using Pythagorean Theorem, in either case, it's pretty quick to how to solve for it. Great. So I'm going to erase the work as I go just so I can keep it all on the screen. All right, so now let's work on finding one of these 2 sides. It actually does not matter which one I start with. Let's go ahead and start with GJ, this side. Here's where I'm going to have to use trig. I know I have to use trig because I can't use Pythagorean Theorem yet. I have 2 unknown side lengths. That's not enough information for me to use Pythagorean Theorem. So I'm going to have to use trig, meaning I'm going to need this mnemonic. SOHCAHTOA comes in really handy. So I like to use the information I was first given in the diagram, this 25 degrees and the 13, for instance. This is the hypotenuse of this right triangle. So in this case, if I'm trying to find side GJ here, relative to this angle 25 degrees, that's opposite the 25 degrees. And I have the hypotenuse already, opposite and hypotenuse. That means I'm going to be using the S for sine. So the sine of 25 degrees is going to equal opposite over hypotenuse. The opposite is the side I'm solving for here, the GJ side. And then the hypotenuse here is the other piece I was given, that 13 units. Great. And so now to solve for this missing piece, I need to move this 13 by multiplication to the other side. I'm going to get 13 times the sine of 25 degrees is equal to side GJ. That can all be done on a calculator, or a computer for that matter. But I would start with the sine of 25 degrees. Gives me this ungodly decimal. Just don't forget to multiply it by that denominator that I moved out front. Oh, sine 25 degrees, and then multiplied by 13. I get rounded to the nearest tenth. You will be asked to round to the nearest tenth on this one, is about 5.5. Great. Another piece done. So side GJ, about 5.5 units. For the record, I could use Pythagorean theorem now to solve for this third unknown side. Now that I know the hypotenuse and one of the legs, I could do 5.5 squared plus my unknown side squared is equal to 13 squared, and just do some arithmetic with that. For the sake of doing a little trig practice, I'll go ahead and use trig to solve for this third side. All right, so again, using my SOHCAHTOA, now if I need side HJ, this one up here, notice it's adjacent to 25 degrees right here. So my adjacent side, I still know the hypotenuse. So I have the adjacent I'm searching for, and then the hypotenuse, that's going to give me the C, cosine of that angle. So cosine of 25 degrees is going to equal adjacent over hypotenuse. The adjacent is the side I'm looking for, side HJ. The hypotenuse is still that 13 unit length. There's my trig ratio. Multiply again by 13. This will look awfully familiar to the last one. It's just a different trig operation. And so again, it can be all done on a calculator. Start with the cosine of 25 degrees, cost button, gives me that ungodly decimal. Just don't forget to multiply by whatever you moved out in front. So in this case, the 13. And I get about 11.8 when I round to the nearest tenth. And that's the third and final side that I needed to find. Again, I should have gotten the same result had I done the Pythagorean theorem. So whatever's most comfortable to you, I just went ahead and demonstrated using the trig ratios. So it's entirely up to you, the technique you use for that last piece of information, whatever you're using. But that will go ahead and conclude our Chapter 9 test preparation. Best of luck, and I'll go ahead and stop recording there.